This is section 12.2, part C, power models. When we apply the logarithm transformation to the response variable y in an exponential model, we produce a linear relationship. To achieve linearity from a power model, we apply the logarithm transformation to both variables. Here are the details. A power model has the form of y is equal to a times x raised to the p power, where a and p are constants. Take the logarithm of both sides of the equation using the properties of logarithms. So we'll take the log of the left, so we'll have log of y equals the log of a times x raised to the p power. Now this is the same thing when we have multiplication when you're dealing with logarithms. So right now we have a times x. By the rules of logarithms, multiplication can be separated into addition. So instead of the log of a times x, now it's going to be the log of a plus the log of x raised to the p power. And when you're dealing with logs, anytime you have an exponent, you can bring it out front. So this will equal the log of a plus p times the log of x. So the equation of log y is equal to log a plus p log of x shows that taking the logarithm of both variables results in a linear relationship between log of y to log x. Look carefully. The power p in the power model becomes the slope of the straight line that links log y to log x. So as you can see, p is now the value in front of your variable x. So now it is the slope. If a power model describes the relationship between two variables, a scatterplot of the logarithm of both variables should produce a linear pattern. Then we can fit a least squares regression line to the transformed data and use the linear model to make predictions. Here is an example. On July 31st, 2005, a team of astronomers announced that they had discovered what appeared to be a new planet in our solar system. They had first observed this object almost 2 years earlier with a telescope in California. Originally named UB313, the potential planet is bigger than Pluto and has an average distance of about 9.5 billion miles from the Sun. For reference, Earth is about 93 million miles from the Sun. Could this new astronomical body, now called Eris, be a new planet? At the time of the discovery, there were 9 known planets in our solar system. Here are the data on the distance from the Sun and period of revolution of those planets. Note that the distance is measured in astronomical units. The number of Earth's distance to the object is the Sun. So if you notice, this is a curved pattern. The graph below shows the results of 2 different transformations of the data. The graph on the left plots the natural log of the period against the distance from the Sun for all 9 planets, and the graph on the right plots the natural logarithm of the period against the natural logarithm of the distance from the Sun for the 9 planets. And as you can see, the graph on the right is the one that is going to make this linear. So explain why a power model would provide a more appropriate description of the relationship between period of revolution and distance from the Sun than an exponential model. So the scatter plot of the natural log of the period versus the distance is clearly a curved model. If we come back up here and we look at this scatter, if we just take the log or the natural log of just the distance, we're still getting a very clearly curved pattern. But if we take the natural log of both the distance and the period, we are getting the straight line. So it is more appropriate to have a power model. Manytab output for a linear regression analysis on the transformed data when the natural log was taken on both variables is shown below. Give the equation of the least squares regression line. Be sure to define any variables that you use. Now remember, when you're doing this, we can just say like the ln of y hat is equal to, and then go from there. Or you can go ahead and define your variables in your equation. And if we do that, we're going to say the natural log of the period with a hat over it, because it's the predicted period, is equal to our constant plus our slope times the ln of the distance, or the natural log of the distance. Use the model from part B to predict the period of revolution for Eris, which is 9,500,000,000 divided by 93 million, or 102.15 astronomical units from the sun, and show your work. So because we have our distance in astronomical units, we're going to take that and we are going to plug that in for our distance. When we do that, so we're going to plug that in, and if we put this part into your calculator, you're going to get 6.939. So we know that the natural log of the period is equal to 6.939. If you remember when you discovered or went over logs in Algebra 2, the natural log is the same thing as log base e. Now to get rid of that e, to get rid of the base, we can make that the bottom for both sides. So we can say e raised to the ln of the period is going to equal e raised to the log base e of the period. Now the e and the ln will cancel. So you're going to be left with, we're going to put that over here. So we're going to be left with that the period, because the e and the ln have canceled, you're just left with the period, is equal to e raised to the 6.939, or it's going to take it approximately 1,032 years to make a revolution. A residual plot for the linear regression in Part B is shown below. Do you expect your prediction in Part C to be too high, too low, or just right, and justify your answer? So Eris's value for the natural log of the distance is 6.939, which falls far to the right. So our residual only goes to 4. 6.9 would be somewhere all the way over here, where all the residuals, if you notice, anything over here is positive. Now we know that residual is the actual value minus the predicted value. So it seems likely that we're also going to have a positive residual. So since it's going to be positive, if we do actual minus predicted, we would expect that our prediction would be too low. We have used statistical software to do all the transformations and linear regression analysis in this section so far. Now let's look at how the process works on a graphing calculator. We will use Planet data to illustrate a general strategy for the performing transformation with logarithms on the TI-84. A similar approach can be used for transforming data with power and roots. So we're going to enter the values of the explanatory variables, which is the distance, into list 1, and the response variables, or the period of revolution, in list 2. You're going to make a scatterplot of y versus x, and you're going to confirm that we do have a curved pattern. Remember, you need to hit second y equals, turn your stat plot on, and make sure it's a scatter plot. I would go to your y equals, make sure that's cleared out, and then if you hit zoom and select option number 9, which is zoom stat, it will change your window so it will fit your data. Next, we can define list 3 to be the logarithm. It can be either base 10 or base e of L1. So if you go over to list 3 and you highlight it, you can hit ln and it'll pop up with parenthesis, and then you can select list 1, close parenthesis and hit enter, and it'll take the logarithm of all of list 1 and put it into list 3. And then in list 4, you can do the same thing, just make sure you use the same base. So you can either use regular log base 10, or you can use the natural log, which is ln. But whatever you do for list 3, you're going to do the same thing for list 4. And list 4, you're going to take the log of list 2. To see whether an exponential model fits the original data, you would plot list 1 against list 4 and see if it's linear. If it is linear, that means it's an exponential model. If that's not linear, you can graph list 3 versus list 1, which would be your two logs against each other. And if that's linear, you know you have a power function. We will use the planet data again. So if a linear pattern is present, we can calculate the equation for the least squares regression line and store it into y1. In this case, it was a power function and not an exponential, so we're going to use list 3 and list 4. So if you go to your calculator, you hit stat, you go over to calculate, you're going to calculate a linear regression in the form of a plus bx. And this time, you're going to need to make sure that your x list is for list 3, your y list is for list 4. Now, to get list 3 and list 4, you just hit second and the number 3, and then second and the number 4 to get list 4. And we're going to store it into y1. Remember to that you'd hit vars, go over to y vars, select function, select y1, and then you can calculate, and it will give you your equation for the linear regression using those logarithms. If we need to construct a residual plot to look for any departures from the linear pattern, for the x list, you would enter the list you used for your explanatory variable in the linear regression calculator, and you can make a list of the residuals for the y list. Use the residuals list. So for the planet data, you can use list 3 as your x list. To make a prediction for a specific value of the explanatory variable, x equals k, modify the regression equation in y1 by changing x to log x or the natural log of x, if applicable. Then use y1 times k to obtain predicted values of the log of y or the natural log of y. To get the predicted value of y, you're going to use 10 raised to your answer if you used log base 10, or e raised to your answer if you used natural log to undo the logarithm transformation. Here's our prediction for the period of revolution for Eris, which is at a distance of 102.15 astronomical units from the sun. So they plugged in the value into y1, and they did y1, they're plugging in the distance of 102.15, and they're going to get an answer. Once they have that answer, since this was done in natural log, we'll do e raised to that answer, and you will get how long it would take to make a revolution.